So far, we have discussed the electron configuration, the valence electrons, chemical bonding. It's either ionic or covalent bonds. Then we have the electron dot structure, and then the VSEPR theory. Let's see how these topics are connected. Again, this is chemistry, and chemistry is concerned in the study of things or matter. We have different types of matter, and the purest types of matter, we call them as elements. So we have 118 different kinds of elements right now, and these elements are the building blocks of matter. So they make up everything that we are familiar with. Well, most things that we interact with are actually combinations of these elements. Example, water. Water is not a pure matter. It's actually composed of two types of things. It's composed of a hydrogen gas and an oxygen gas. So elements they tend to react, or they bond or they combine with other elements. Example, sodium. Sodium, actually, it's very rare to find a pure sodium because naturally sodium is very reactive, so it combines with other elements. Example, sodium is found on table salt, and in salt, sodium is not alone. Sodium is bonded with chlorine atoms. So we'll see how these elements combine and why do they bond to other elements. We'll see that one in this lecture video. Of course, it has something to do with their atoms. Again, based on the atomic theory, all elements are made up of atoms. We have, let's take for example, H2O or water. So this molecular formula presents that water is composed of two hydrogen atoms, that's this one, and one oxygen atoms. Again, these atoms are bonded to each other. So this can be the structure, and this can also be the structure. So which one is correct? So we'll follow some guidelines. The central atom should be the atom with the lowest electronegativity. So for that one, we'll try to check their electronegativity. The electronegativity for oxygen is 3.5, and the electronegativity of hydrogen is 2.1. So which one has the lower electronegativity? In this case, that's hydrogen. But we have a rule here, except hydrogen. So hydrogen will never be the central atom. So we only have two types of atoms here, and again, hydrogen cannot be the central atom. On this case, the oxygen must be the central atom. So this one is not the model, but this one. So we'll take this one for now, this H2O. Okay, so for us to better understand this molecule, let's start with its electron configuration. So the electron configuration simply shows how the electrons are arranged inside the atoms. So for example, hydrogen, then we have oxygen. Hydrogen have how many electrons? That's one electron, one valence, one electron. Then next we have oxygen must have eight, eight electrons. And again, these electrons are distributed on different orbitals, subshell. Hydrogen, so it is only one electron and it goes on the 1s orbital. Okay, that's one energy level, and on the s orbital, that's 1s1. Again, the exponent presents the number of electrons. So we have for hydrogen, we have 1s1. So this means that there is one valence electron on the first energy level, and it's on the s orbital. Next, we have the oxygen. It has 8 valence electron. So where would the first val electrons go? That's 1s2. Again, only 2 can occupy the s orbital. So next we have next energy level. We still have 2s. We have 2. It's now full. We'll go to the 2p. 2, 4. We have 4 electrons left. So that's the electron configuration of these elements. Let's check their valence electron. The valence electrons are the electrons found on the outermost energy level. Let us check for hydrogen. Hydrogen only have one electron and it does only occupy the 1s orbital. So therefore, the outermost orbital or the energy level is 1 and it has only one electron. Hydrogen have one valence electron. For oxygen, its electrons occupy the first energy level and the second energy level. So the outermost energy level is the second energy level, and the second energy level have 2 plus 4, that's 6 valence electrons. Again, valence electrons are the one involved on chemical reactions or on chemical bonding. So again, let's take note for that. Hydrogen have one valence electron and oxygen have 6 valence electrons. We have discussed that. Again, we can see or we can have a shortcut for this. Just look at their location on the table of elements. Hydrogen is on group 1. It has one valence electron, and then oxygen is found on group 1, 2, 3, 4, 5, 6. Therefore, oxygen has 6 valence electrons. Okay, we have H2O. Let's go back to the solution that we have, H, O, and H. The next step is to make sure that the terminal atoms are happy or satisfied. On this molecule, we have the central atom is the oxygen, and then we have the terminal atoms, the H. They are found on the terminal or on the sides of the central atom. So, in this case, hydrogen have one valence electron. Also, hydrogen have one valence electron. So how can we make hydrogen happy? We give one more electron. In this case, it shares an electron from oxygen. So it forms single bond. Okay. So is hydrogen happy now? Yes. Again, hydrogen is happy when it has two valence electrons. And for oxygen, that's 8. That's the octet rule. 1, 2. Okay. And let's check. So this model must show the valence electrons of an atom. Oxygen must have 6 valence electrons. So that's 1, 2. We still have 3, 4, 5, 6. So these have 6 valence electrons. And overall, 1, 2, 3, 4, 5, 6, 7, 8. So all atoms on this molecule is stable. So we have here the electron dot structure for H2O. Next, let's see whether this is its molecule.